good? Yeah, okay, I'm gonna share the notebook. I actually haven't tested it out on like, let's say like my own data set. I was kind of running through it to figure out how we can use it, since there were some questions or interest last night of how to, I guess, use these images in a 3D way. And what's interesting about NERF is that, so I'm sharing in the chat. But what's interesting about NERF, or the NERF approach, is that you can feed it images, and it'll generate, or it'll learn to generate like some sort of object from those images and be able to build either like a depth mapping from those images. It's kind of like photogrammetry in a sense, where you have like images from different angles, and the algorithm figures out like which points match up in space, and it's able to generate an object from that, and then you can generate novel camera views from that. So I'll just show you how to run the notebook if you guys want to try it. And there's some explanations within the notebook itself that shows how to insert your own data. So this is a notebook. It's called NERF and there's like several NERFs, let's say, approaches that have been developed in about the last, I guess, year or so, and became really popular after a presentation last year in CVPR. And what it does is like, it's the idea of neuroradiance fields. And if you, let's say, go to the page here. So essentially, like, you can take images from different angles, and then it learns to generate a depth map. And the way that it does it is it shoots rays from all the images, and those rays intersects, takes the opacity and the color. And just by doing that, it's able to pinpoint in space where it's located, or where this, let's say, pixel is located. So that's kind of a fascinating approach. And you can see here some of the videos that these people, or the creators, generated. So these are novel render views from these images. And you can see like it actually achieves like pretty high level of detail. And what's interesting about this notebook specifically, and why I chose it, is because this one doesn't need as input camera parameters as like some of the other previous NERF models do. So this is open for experimentation. I haven't really gone into it, but so if you guys want to take this and test it out, like this notebook, I just share the link, and you would run it the same way. You can sort of run through the code, run all these cells. This is going to download the model from the GitHub page. And it also has some scenes that they have, like kind of like sample data sets that they use. And you can run through all this. And then here in this part, it explains like how you can input your own data set. So like if you want to try your own images, you can input your images. It's gonna be in, I don't have the notebook here, but it tells you like how to upload them. And it says like you need about 20 to 60 forward-facing images in LLF fashion. So I showed this video earlier, but this is kind of what they mean. So if you want to try it out, you would need images like this. But obviously, if you want to use like images from like that were generated from the VQGAN, from some sort of panning, you can test those out and see what you get as an output. So once you do that, you can just run through it. The notebook, it's pretty self-explanatory. They have commented a lot of things in. And then, for example, here's like the input image. Is there a question? LF fashion. So LF fashion, I'm not sure exactly what it means. It might say somewhere in the paper. I think it is related to, I think it means like it's related to how you would take the image in the sense that you can map it. So if you take it in that order, let's say how they're showing here, it allows you to have some sort of intersection of pixels within the images, and that's how it's able to build the sort of representation. Um, but I'm not sure exactly like what's the definition. I haven't really looked into that deeply. So yeah, so if you take that and for example, you feed in this sample image, this is like one of the images that they have of a desk. And you're gonna take this image and they have about, I think 48 images total of this desk from different angles. And then you would just run this and train it. So this is the NERF model here. This is their NERF model. It's a tiny NERF, and this they made it smaller so you can run it on Colab, so your Colab doesn't run out of memory. And go through the notebook. This is a part where, so this is like kind of like the most important part of how NERF works, where this at every let's say time step that you process, let's say you run a forward pass on the network, is going to generate like a view from an angle, and then it's going to test that view on the say the ground truth images. And once it does that, then it's able to learn from that, like let's say the difference between the view that is generated and the ground truth image. And then it'll learn from that, and it'll run through all the images until it has a pretty good let's say or until it lowers the loss function to a point where it looks pretty accurate. And then you can go through this, and then this is, all right, so this is TensorFlow. This is just for logging like your data, the loss function. And then as you keep going here, you can set the number of epochs for training. So they said you can do 1,000 to get a decent results, and then they use 10K in their paper, but that obviously is going to take more time. Eval interval, it says render an image to visualize for every interval. So this is like every 50 iterations you want to generate an image or a novel image. And then you can just go through, and then it'll run through the training process. And once you get that, this is to generate the novel image. So then you can get this, and it generates like a GIF. And this image is supposed to be from a camera view that it hasn't seen before from the original data set. So that's what makes it interesting, where you can get now like a completely generated three-dimensional scene from a camera input that you want to input. And then out here, it just plots like where the camera is kind of like located in space and where it's taking those views from. So yeah, if you guys want to try this out and like see how it works, you can also go into their project page and like read more about it. But it's a very recent approach that people have been taking, and there's already a lot of papers that have been coming out that show how these approaches can be used to generate like 3D models, and how to generate like geometry that is way like has much better detail than like other sort of photogrammetry methods. So yeah, so that's what I wanted to share.
Any questions?
Isn't this the notebook or the method that like you get pictures of it and take a 3D model out of it? Is this approach? Can we do something similar with this notebook? Like if you get a camera, record a video like going through an object, and then you split the video into frames and feed into the algorithm and get like the 3D out of it? Do you think it's possible?
Yeah, that's what it's doing. So let me see if I can.
Because like I was wondering if I can do this, or if I can just like stand with the camera and like take picture, or I can like record the object and get the frames of it and feed there.
Yeah, so you can do that. And it's sort of like you have to like test it out because they do recommend like a lot of sort of images, right? Like and one of the like you can do a video, right? Like you take a video and it's gonna sort of get you like some sort of object out of it. The only thing is like depends, like if your image, like your original, like say ground truth data set has some occlusions or something like that, then you might not see that. But what they've been trying to do with the NERF model and what kind of separates it, say, from like traditional photogrammetry models, is that there's a possibility since you're using a neural network, the neural network is gonna kind of generalize, right? Or that's kind of like the purpose of it. So it's gonna try to like predict what's behind those occlusions somehow. And if you train it on a decent amount of data, it should be able to give you a decent result. And like I've been trying to follow it, but there's been like a lot of papers recently that have been coming out that people have been taking this approach and try to make it work as best as they possibly can. So there's obviously like a lot of literature you can look into, but it's kind of fascinating that and like the cool part about it is like if you can hook this up now in a generative manner with let's say like a clip or something, then you have the possibility to get out some sort of three-dimensional output. So that's kind of an interesting idea or thing to think about.
Yeah. I think this
Hey,
could, it could,
I don't know if
Oh.
this helps, but Ricardo, if you want to generate like a 3D model using just these pictures, I think you could just look at Autodesk Recap. So you just upload the pictures and it generates a 3D mesh model that you could upload to any other, probably Rhino. And it gives you a pretty okayish detailed model. I think the details it lacks, but with the textures as well. I don't know if this helps, but you could look into that.
thank you for the indication.
Okay. Two things I would like to share is first, the NERF model is revolutionary in one sense. It's just a multi-layer perceptron. So it just takes X, Y, Z camera angle in 2D plane, theta, and phi in 3D plane, and outputs like for each spatial element RGB, like the color, and the density. So I was in one of the discussion in the famous conference, and like there was one point where like, why do you need 3D model if you can synthesize all the views from all the angles and generate it? It, it even questions the need of it. So for image to 3D, I think I had a script where you just take one image, generate depth map, and then generate point cloud. And if you guys are interested, I can share it with you later. But it it's the same. Like the concept is important. Where in the way point cloud work is, you need RGB data, and also you need like the depth data. So you can't generate like point cloud just from an image. You need to generate depth map first. So and there are like software which can also do, but if you want, um, let me check if I have a short clip. Yeah, there was one image where, yeah, so here, oh man, I'm using this machine learning library to create depth map from single image. And then I'm using a open source library called Open3D, which is generating point cloud from depth map and RGB data. And you can see this is the input image, this is the depth map. And this is the point cloud 3D data it's generating. But this is the workflow you can follow if you just want like single image to 3D. Cool. I have something exciting for you guys. So we saw on that day that GPT-3 was doing some amazing results. So we using GPT Neo, like anyone can access this model. So oops. It's gonna take time for you guys to install, but I'm gonna show it's same. You can just click play all, and it will take a lot of time to download this model. You can see like it's 1.3 billion parameters. So special thanks to Illuthor AI for making this accessible. And yeah, one thing I wanted to mention, like if you're sharing stuff on all of the media, it's a recommended practice that you credit the owner, because many times there's also a debate on Twitter going on that many people create AI artwork, but then discredit like the person who gave the script. So it would be good if we can credit them. So yeah, so it's basically downloading the model, and this is, we are doing auto-regressive text model. So here, like if you are just playing, I'm just giving a prompt and I'm giving like minimum and maximum length to generate the whole regressive part. And you can, if anyone has any suggestion, I can type it to test. Okay, the future of architecture, let's say. And if we run it, come on. Okay. I should have decreased it. Right. Okay, it's saying it's coming to the city and the best ways to embrace it. Yeah, so you can define the minimum and maximum length of the essay, and this gives like first text completion. So you can use it in literature study or precedent study, but it's just a example of like what Veronica was suggesting, or auto regress. The cool part is I can even ask the model to write a code for me. So here I wrote like, give me a view. So Vue.js is a JavaScript library for designing website, and it gave like all the HTML prompt and style. So it's just amazing. I can also write, let's say, CSS code. We can just move if it's gonna take time.
But if you get like, if you ask for a code for a specific objective, does it like solve the problem? For example, oh, bring me a loop for iterating in a folder and copying whatever. Like I know GPT-3 can do it, and
Yeah,
have you
so
tried something in Python?
yeah, let me check. Okay, I'll change this length to 50 and 100. So let's say
Python code.
give me a Python
A Python code.
code to run a loop.
Yeah.
Or create a loop.
There's actually something recently that I think OpenAI just came out with, that it's like, it's kind of like you tell it like what you want it to code, what your output is, and like it'll do it. And like they just, I don't know if they released it out yet or it's like still in like in a beta phase, but it's like a new product that they just came out with. So that's kind of like, I guess that's the point, right? Like and it was trained on I think it was like GitHub or something like that. Like
Yeah,
all the
yeah.
code that exists on GitHub.
Yeah, I applied for the test version. Let's see if they can give me access. So they released AI pair
Yeah,
programmer. So you can just
this is
from the
wild.
definition, it's so yeah, for folks who are just starting programming, days are near where it's not gonna be that difficult to do programming. Okay. Okay, it's for I in item product.
Yeah.
Dang. Okay.
It works. That's wild.
That's wild. Okay, so okay, even for code it works. It's things are going pretty fast in AI world.
Yeah.
Or so have fun experimenting with this, and I shared the script with you guys. Another thing is autoregressive. We saw text in image, and I would ask like it's gonna go very technical. Like there are different ways. Deep generative models are done, like the categories. Oh, come on. No, not this one. Yeah, this one. So like even in generative model, there's explicit, implicit density, then tractable function, and PixelR CNN falls under this category, and GAN are under this. And there are like it's this one which we're gonna do is like flow-based modeling. Okay, not this. Where is? Okay, this one you can try it. Okay, anyone with the link? Copy. Cool. So I shared that. So the way it works is initially the first idea was PixelRNN, where uh, it takes like all the pixels before, and it's if you know like conditional probability. So when it's starting here x2, so what's the probability of x2 given x1? When it goes for x3, what is the probability of x3 given x2 and x1? So it's builds like a conditional probability, and it's called flow based generative modeling. There are like other techniques. And it learns like the likelihood of prediction. So it's different compared to like VAs or GANs, and you can't like it doesn't have that latent representation where you can like here you can inverse the flow function and find the output. There are also like Pixel CNN was discussed. The challenge with Pixel CNN is there is a area. Okay, here if you work with language models to make it for sequence to sequence, they use like a masking technique to make it autoregressive. So here they are using disk mask for the kernel and they're going through the image. But for pixel RNN, like they found this blind spot in this receptive field. So imagine like this is your kernel. These are all the ones, these are zeros. For first run, it will go through this. For second run, it will do that receptive field, and third run that. So there's all these pixels which whose context was not added for it. So to avoid that, they came up with horizontal and vertical stack, where they had like this kind of 2 by 3 filter instead of 3 by 3, and that's all the problem. And I'm not sure if the script has this. And yeah, so here they're just showing examples of receptive field and how it's going bigger and it's adding the context. So also if one way to imagine convolution, like the ultimate one of the goal is finding relationship between parameters in your input of AI model. So if you pass an image through a convolution like neural network, whatever it is. So ultimately when the image goes inside the convolution and goes smaller and smaller, if there is like a human face, cycle. You want to get relationship between human face and the cycle. But if your kernel size is small, you only get the local context vector. But so in the first few layers inside the convolution, this information has not been correlated with this. But then once the image gets smaller in the convolutional like size also becomes significant part of that image, then like this dog or any other object starts relation between different objects in the image. And yeah, the relationship between various variables in the image is what we want to extract from the model. So that's the in convolution, the kernel size defines the receptive field. And here you can see with various iterations, this is the receptive field. So I can see all the things which are like if it's a sentence, I can see all the words before and I can predict this the next word. Here I can see all the pixels before and I can predict the next pixel. So yeah, and then there is another model called gated pixel CNN, which avoids this problem and where it predicts like the pixel beneath when it gives that jump. Yeah, this is the gated. One quick, okay, they don't have here. There was a demo where they had like digits, MNIST digits, where let me see why it's not here.
Is this the one where you can like draw, like it kind of draws them? Like that example, where like it'll draw like the digits or somehow instead of like if you do I guess another method, it does the whole image at once.
Yeah, so I thought I had that example where uh this is basically what they did here was after training the network, they just like masked all this, like just gave like half of the image of the number, and it as output it gave like auto completion of whole 7. So that's like masking image and it auto. But the challenge there was like first like they generated like in that example 8 by 8 pixel image. It took like 30 seconds. Then they generated 28 by 28 image and it took like 4 minutes. So using this auto regression models, it takes a lot of time for sampling the output. And that's one of the reason it's relatively less popular than other generative models. So that's overall idea I wanted to give. I thought this had, let me get back to you where I was able to generate MNIST digits. Pixel. Is generating. Okay, yeah. It was this one. Yeah, so in regard to how you can, yeah, so if you want to do custom like training, you need to like custom image completion, you need to do training first and then you can use this. And I'm not sure. So have you seen Sketch RNN? It also works on using RNN to complete. Yeah. So I had this idea. I want to train on architectural sketches to do
Mhm.
completion. It's also, yeah, human machine creativity, as you can see here. Cool. So in this collab, yeah, basically this is just for testing. If you want to train it for architectural images, you need to modify it. Cool. I hope you found this interesting. Dude, maybe it looks like after experimenting with VQGAN and Cliff, they don't find other stuff that interesting.